It's a subject I hope to see in the educational system in Western schools one day, that people are told that the plate tectonics theory is incomplete and needs to be seen in a larger framework. So that was the reason I've got Dr. James Maxlow over here from Western Australia. He's internationally recognised in this field. He's part of a huge network of people researching such things. He's here today to show you visually and tell you all the mechanics of why and how our Earth has been expanding and where it's going. Please give James a big, warm Nexus Conference welcome, James Maxlow.
Thank you, Duncan, for that glowing introduction, and good morning, ladies and gentlemen. I guess my contribution to this conference today is to move away from the metaphysical side of science to the more physical sciences, and this is my speciality, of course, Earth expansion. My background is that I'm a geologist, and I've been working in the mining industry for all of my working career, mainly looking for that dumb yellow metal, as we all seem to want and admire. I currently operate through Torella Consultants, my own company in Perth, Torella Consultants. And I guess my interest in Earth expansion stems from about 1980, when I came across a little book by the late Professor Sam Warren Carey, who's the father of, considered the father of Earth expansion. I later met him in Perth at a conference in the University of WA in 1988, and then was so inspired that I commenced a master's research at Curtin University in Perth in the early 90s, and then moved on to a PhD study in the late 90s, culminating in this, what I'm about to show you today. It also culminates in a publication of my book, Terra Non Firma Earth, Plate Tectonics is a Myth. What I'll be going through today is to just give you a rundown on what evidence is there to suggest that the Earth is expanding. As Duncan alluded to, we're stereotyped into thinking that plate tectonics is the answer to all things global, and this is to the detriment of these alternative theories that have been around for quite some time, and also other theories as well as this one. And I guess that also leads us on to the ultimate question is what causes the Earth to expand, and unfortunately human nature decrees that we must understand the cause of things before we understand the physical side of things, or want to comprehend the physical side of things. I'm going to leave that question till right at the very end, and I ask you just to simply dwell on not consider how these things happen, just look at the coincidences that of this reconstructions that I'll be showing you, and see how they fit in, and see if you agree with me that yes, the Earth is expanding. The concept of Earth expansion has been known about for in excess of 70 years now. Otto Hilgenberg from Germany was the first person to make small Earth models, and he recognised that if you take the area of each of the oceans away and just leave the continents, each of those continents can fit together like a spherical jigsaw puzzle at around about 55% of the present Earth radius. Being early 1930s, of course, both his ideas and his little book called The Expanding Earth were neglected, and unfortunately it lay dormant for quite some time. The next major contribution was Klaus Vogel from East Germany in 1979-1980. He again made a number of models, small Earth models, about to here on my model, somewhere in there, and this represents about, say, 200 million years of Earth history, about 4% of total Earth history. Klaus was fortunate that in that mapping of the oceans was just starting to become available, and he was able to quantify his models using this data, and also our concept of plate tectonics was firmly established in that we now understood that, yes, the continents could move around the Earth. In Hilgenberg's days, it was considered the Earth was fixed, all the continents were fixed. And I'll just digress slightly. In Hilgenberg's day, in fact, right up until maybe even present day, a lot of people consider that the continents and ocean crusts are one and the same, and the oceans are simply oceanised continents. In other words, continental crust covered in water. And this is, as I'll show you, this is just simply not true. My own research comprises a series of 24 models, 5 of them shown here, but we'll get to that later. 23 from the present day, this one here, back to the beginnings of Earth history, 4,600 million years ago. And then one model also projected to the future, 5 million years into the future. This research has been, I've been very fortunate. This research coincides with modern, huge, big global data sets in geology, geography, geophysics and so on. And also coincides with modern computer technology and software and animations, as I'll show you here. My own modelling represents 100% of Earth history, and this is the very first time that modelling studies have been projected this far back for any concept. Plate tectonics, for instance, only goes back 20% of Earth history, and they struggle to get back to 20%. It's not convincing at all. Yep, and as I mentioned before, this culminates in publication of my book, as we'll deal with later. My own model studies coincide with publication of this geological map of the world. And this mapping was not available to my predecessors. And it was primarily mapped, it was undertaken to quantify plate tectonics. But unfortunately, as I'll elaborate, this did not come anywhere near quantifying plate tectonics. In fact, this information is rarely to never used in plate tectonics anymore. It has provided a unique tool to Earth expansionists like myself to quantify the Earth expansion process. The colours shown in this map represent intervals of geological time, and as should become immediately apparent, the colours in the continents have a different fabric, a different texture to the colours in the oceans. Each of these colours, as I said, represents an interval time, an interval where sediments are being deposited, extruded or extruded in volcanism, for instance, over a set period of time. It doesn't discriminate between, say, granites or volcanic rocks or sedimentary rocks. It's just a package of rocks which were formed in that period of time. The continents comprise these very ancient fragments, the granites and volcanic rocks shown in pink and red, very ancient sedimentary rocks shown in khaki, and progressively younger sedimentary and volcanic rocks shown in blues and yellows, I think, in there. This is as distinct from the oceanic crust, and as I intimated before, continental crust is quite distinct, is quite different to the oceanic crust. Continents are around about, say, 30 to 70, 80 kilometres thick on average, whereas the oceanic crust is only about 7 to 10 kilometres thick, and the oceanic crust is primarily volcanic rocks. What you can also see, and find the cursor again, is that each of the oceans contain, or the colours are symmetrical about this central mid-ocean rift zone. You may or may not have heard this term, mid-ocean rift. I have this in spherical format in the next slide, but this can be visualised as a network of cracks networking all around the world, centrally located in each of the oceans. And this was quite a revelation to the map makers, the oceanographers and geophysicists when they were mapping this. So what this, you may or may not have seen footage on television of the deep sea submersibles going very deep in the oceans and these black smokers coming out and the super hot steamy water and all the mucky metals and whatnot. That's where these occur along these mid-ocean rift zones. You also see that the colours graduate away from that central mid-ocean rift zone. So the central, we'll focus on this area, this central pink colour is present, occurring right now to about 2 million years ago. As we move away, these volcanic rocks age away from this mid-ocean rift zone to this blue colour, which is the early Jurassic, about 165 million years ago. And these are the oldest oceanic crusts in each of the oceans. I thought it didn't behave itself there. Okay, this is the same data portrayed on a spherical Earth. It's here. Damn. Stephen, please. Yeah.
That's it. Thank you.
Yeah, it should rotate though. Oh, wrong one. I'll talk through this one while Stephen comes. The Earth is a sphere, as we all know. It's not a flat map. The old flat Earth theory has long since been disproven and gone with the gods and whatnot, of course. And this is the same data displayed in spherical format, and as I mentioned, these volcanic rocks age away from this mid-ocean rift zone towards the continents. The oldest shown over here is the early Jurassic. So what you can visualise here is that this is a crack. It opens up, new volcanic material is injected along these cracks over a period of time, along with about, say, 15 to 20% by volume, or by weight rather, of water and volatiles. So all volcanic rocks contain around about 15 to 20% of water and volatiles. So here we have a situation where we have new volcanic rocks being injected along these cracks, along the mid-ocean rift zones, along with an outpouring of the water and gases. Once it hits the water, these volcanic rocks are quenched and solidified. As you open it again, it cracks and further volcanic rocks come in. So this is basically what this striping is showing. So over a period of time, the pink to yellow is around about 15 million years. So in that time, that is cracked and opened, new volcanic rocks come through. So you end up with quite a wide stripe. As I mentioned, this is symmetrical in each of the oceans, so symmetrical about the mid-ocean rift zone. But as I think you can probably appreciate that in order to do this, you then must increase the area of the oceans and move each of the continents away from each other. And this is the basis of tectonics. The Atlantic Ocean in particular is the basis of plate tectonics. I'll move on to the next slide to run down on that. But all of this material is in plate tectonic theory. All of this additional material is supposedly being subducted in the Pacific Ocean, and this is what we're led to believe. Yep, this one works. So what I've done is simply take each of those coloured stripes and remove them, and then fit each of the remaining plates back together at a reduced radius. So it'll go back in time and then come forward in time. And this is quite valid because this material was put there, was in place there during this period of time. So this is future. So all I'm saying is, if you move back in time, you have to take that stripe away, each of those coloured stripes away in sequence, progressively reduce the area of the ocean and move the continents closer together. I'm sure you can appreciate that, and this is common to the plate tectonic theory as well as the Earth expansion theory. The only difference is, with, as I mentioned before, plate tectonics, what you add to the Atlantic Ocean, for instance, you must dispose of elsewhere. In Earth expansion is, as you expand the radius of the Earth, you open up these cracks, new material is forced into these cracks and solidified, and it's simply cumulative with time. So there's no net removal of any material whatsoever. Now, we'll sequence through this, the Indian Ocean as well, just exactly the same. So we'll just sequence through each of the models that I constructed by just simply removing each of these time stripes away in succession until we have a complete continental crust at around about 50 to 55% of the present Earth radius. Now, the Indian Ocean is also the basis of plate tectonics. However, I forgot to mention something in the previous one. This forms a very early basis of plate tectonics, but when you actually physically move each of those continents together, it's the fit together on a static radius Earth is not as accurate as it should be. You can fit together South America against Africa, but then you're left with a great big V-shaped gore in the northern hemisphere. Similarly, you can fit North America to Europe and Africa, but you're left with a great big gore down in the south. What they opt to do, now that this mapping is available, what plate tectonicists do is fit Africa in against the mid-ocean rift zone, and similarly the Americas in against the central zone here. In order to make the continental crust fit with the oceanic crust, they then fragment Europe away from Africa, split it off, and similarly the Caribbean region, split it off, open that up, so these continents are made to fit. And as you can see in this animation on an expanding Earth concept, there's no requirement to split the continents, arbitrarily split and fragment the continents. They just dock back in time, and similarly forwards in time. In real life, of course, that'll be continuous spectrum of models, but 24 models, it tends to be a bit jumpy. Go back to the Indian Ocean. In the plate tectonics, they split Asia and Europe away from the Africa and Arabian Shield areas along the Himalayas and Alpine mountain chain. India is separated as a separate island continent. India is then fitted in against Madagascar, and Australia in against India and Africa in the what's called the Gondwanan configuration, Gondwana supercontinent. You may or may not have heard of Gondwana. Just activate that. And expanding Earth, again, we're just simply taking that volcanic material, the oceanic volcanic material, away in sequence and refitting them back together in a smaller radius Earth. And there's no need to fragment the continents or invoke these hypothetical drifting continents. India, on plate tectonics, is supposedly travels north and crashes into Asia to form the Himalayas. And this is, as you just seen, this is totally unnecessary. Now, as I previously mentioned, all of this material, this new material formed as the Indian and Atlantic Ocean open up, must be disposed of elsewhere in the Pacific Ocean to maintain a static radius Earth. And this is the basis of plate tectonics. This new mapping has only been available since early 90s, and plate tectonics was invented prior to this mapping, and they basically did not know anything about this mapping. So here we have a dilemma. All of this vast amount of new material is supposedly being consumed in the Pacific Ocean, right where in the Pacific Ocean, right where there is an even bigger mid-ocean rift zone, an even bigger zone of new material being exhaled from the mantle. And we'll just sequence back to the present day again. That's Australia and New Zealand against America. This spreading rate, that's the future spreading rate. So the current spreading rate in this East Pacific rift zone is around about 8 to 10 centimetres per year. Now this is about double the rate of the Atlantic Ocean plus Indian Ocean, which is about 1 to 2 centimetres per year. So as I mentioned, here we have a situation where we have this enormous amount of new material, new volcanic material being exposed right where this old material is supposed to be subducted. And that's basically why this mapping information is just not used in plate tectonics. The Southern Ocean is another major dilemma for plate tectonists. In the Southern Ocean, all of the oceans and continents are actively spreading away from Antarctica, away and supposedly moving north into the Northern Hemisphere. And the spreading rate between Antarctica and Australia is around 65 millimetres per year, 6.5 centimetres per year. And as you saw in the previous animations, the Crossland Ocean is essentially east-west, opening up in the Atlantic and Indian Oceans, essentially east-west, and there's no net northern migration of these continents or oceans seen in these animations. There's also, there is no physical evidence for active collision in the Arctic Ocean region with this huge amount of opening of the Southern Ocean. It's got to go somewhere. And as well as converging on the Pacific Ocean for the Atlantic and Indian, it's supposedly converging on the Arctic Ocean as well. And there's just absolutely no record in this region of convergence. Now I've got another animation which may not work, and this is a very important one. What I'm trying to show is each of the globes that I constructed revolving once and then pop down to the next globe. So what I'm simply doing is removing each coloured stripe in turn, popping them down into the next globe and then continuing right through the sequence. Similar to the sequencing slides before, where they just pop through back in time and then come forward again. You do that. Yeah. So what I've done here is simply rotated each globe and then popped down to the next one so you can actually see the transformation back in time and then moving forwards in time. This interval time, the time covered by this animation is about 200 million years, and this represents closing off of the oceans. Remembering right from the start, this Otto Hilgenberg did this visually. We now have this oceanic mapping to physically quantify this closing off process back in time. It represents 4% of Earth history. Our total Earth geological time is about 4,600 million years, for those who don't know. And this 4% of Earth history represents about 70% of the expansion history, as I'll elaborate on shortly. And by using this mapping, I was able to show that each of these reconstructions are latitudinally and longitudinally constrained by the mapping. In other words, there is only one fit option. In plate tectonics, reconstructions are constrained by magnetic data, the location of the poles, the ancient poles, and if you know a little bit about that, their reconstructions are only constrained by latitude and they cannot constrain by longitude, so they have a multitude of fit options. So So any scientist can come in, make a reconstruction and say, yes, this is it, and it'll be completely different to another researcher. On an expanding Earth, we only have one fit option, and this is the key to this presentation, is that you only have one fit option. It is constrained latitudinally and longitudinally by both time and location. In each of the reconstructions, I maintain a greater than 99% fit together in each and every case. Now, this is an impossibility on plate tectonics. There's the Permian period, about 250 million years ago, and it is the next globe down from the previous set of globes. It represents the ancient Pangaean supercontinent. I hope you've all heard of these terms, Pangaea, Gondwana. You probably haven't heard Rodinia. And on an expanding Earth, this represents the time when all of the oceans have been removed and we have a complete continental crust encompassing the entire Earth, and in this particular model at around about 50% of the present Earth radius. There are no modern oceans. All we're left with is all of the volcanic material that was previously injected into the ocean crusts has been returned to the mantle, along with the majority, most of the ocean waters and atmospheric gases. The exposed lands in this case, as I mentioned, is Pangaea, and the little continental seas will just sneak around the corner. This represents the ancient continental coastal outlines. So the larger areas are the lands, and the smaller areas encompassed by that blue line is the shallow continental seas. These are referred to as the Tethys, Panthalassa and Iapetus seas. You may or may not have heard these from plate tectonics. In plate tectonics, these are actually called oceans, and these are huge, big inferred oceans with these fragmented continents surrounding them. If I could squeeze around there, I could show you the location of the present continents. Just take note of the two white areas. The pointy one is Greenland, and the large white mass is Antarctica, and next to Greenland is the Bay of Hudson Bay from North America. The Greenland and Antarctica, of course, are presently covered by continental ice sheets, and we just don't know what the geology of these areas is. So it's a good reference point to locate yourself. That's Antarctica, and the red line. Sorry about that. I'll have question times at the end, and that'll come into it. Yeah, the red line across the middle, of course, is the equator, the ancient equator, and that's Antarctica. Throughout the remainder, moving back in time, the remaining 95% of Earth history, this is where all of the continents were located, Antarctica straddling the equator, as distinct from the pole, where we're supposedly led to believe it was at the time. Now, basically that sequence of animations was the basis of my master's research, just reconstructing the configuration back to that Permian period using oceanic mapping to quantify each of those globes. This is a mathematical representation of radius. Determining an ancient radius is very simple. You just simply measure the area of each of those coloured stripes and convert that to radius. And when you plot them as a graph. They plot down this side here, and as you can see, this matches in precisely with Klaus Vogel and also Jan Kozier from Poland, who had access to this early versions of this data. Our more distant researchers were not privy to this data, so they weren't constrained, time-wise they weren't constrained, but it still shows an expansion there. My PhD research then took that step further, which we'll lead on to next, by using the continental crust to again define the change in radius with time. This curve, for those mathematically inclined, this curve is an exponential curve. An exponential curve has a very, very long and slow, steady lead up, and then a steady to accelerating increase up to a rapid increase, as shown here. Don't be too alarmed. This is, what, 2,500, so the actual age of the Earth is way back here, the origins of the Earth in the Archean, early Archean. The rate of increase from there to there, which is 75% of Earth history, is about from 0 to 100 microns per year, and the thickness of a human hair is around about 100 microns. So for that protracted period of time, we had less than the thickness of a human hair, this increase in Earth radius. From there, we had a steady to accelerating increase up to the present day rate of 22 millimetres per year, about this much, less than an inch. So when you relate that to time, it is next to insignificant. And for those of you who have travelled overseas, travelling from here to Europe, for instance, you would hardly flinch at 22 millimetres increase for each year. Projecting this to the future, within 300 to 500 million years into the future, the radius of the Earth will then reach the same radius as Jupiter, the giant planets Jupiter and Saturn. You can visualise the Earth as being a wet planet, and this is distinct from the giant gaseous planets and the smaller inner rocky planets. So the Earth is, to my way of thinking, is in a transitional phase between the rocky planet status to the giant gaseous planet status. So as the radius of the Earth increases, we have an increased outpouring of the volatile gases and the waters, and eventually this evaporates to form a huge gas cloud surrounding the primitive, or the remnant Earth at that time, similar to Jupiter and Saturn. We'll probably develop rings and all that sort of thing as well. At that time, I envisage the actual expansion process will then stop for reasons we'll elaborate on later. And of course, life as we know it will, of course, long since have been deceased and evolved or progressed into something better than what we are now. This next slide is an introduction to the next phase of this presentation. What happens to the continental crust, and in part the oceanic crust, when we increase Earth radius? And this is alluding to a mechanism for mountain building and seismic activity and volcanic activity, etc. Shown here is a cross-section of a primitive Earth, the Permian-Pangean Earth, at 50% of the present Earth radius, and the present-day Earth. I've also shown a fragment of a primitive crust, just one small fragment, and this is about 5,000 kilometres diameter, about the size of the present-day European continent. I've omitted, for clarity, I've omitted the rest of the crust. So what happens when we increase radius is we get a progressive, we'll just see if that animation works, yep, we just get a progressive flattening of that surface curvature. Now this is a very important point to accept. is that you get a flattening of this surface curvature and also an extension of that component, that radial component through here, sorry, the chord length through here. This doesn't happen all at once. It happens over a projected period of time, over that full period of time. The elevation, the difference in elevation we're talking about is around about 580 kilometres of this material must collapse, progressively collapse. So as the Earth progressively increases in radius, you're getting first off, you're getting a slight super elevation of the continental material. As you get both sets of both crusts joined together, you get a super elevation in the continents, hence the continental crust. The primitive continent, supercontinents, and within the adjoining areas, the areas of the continental seas, the depressed areas. As you then progressively flatten that crust, you get compression within those continental sea areas, compression, folding of these soft sediments, any jostling, you get mountain building and volcanic activity, and also introduction of metals and granites and volcanic rocks. I guess this is what I find throughout history, is that this is generally pulsed. You get super elevation, collapse, and also erosion of that crust, the elevated crust, and weakening of that central area, and collapse again, compression to form your mountain belts, extension, basin forming, sediments, new sediments, compression to form new mountains, and so on. We'll just hone in a little bit closer to, and this is a schematic representation of what happens to the crust itself. Now, what's shown here is the continental crust, about 30 to 70, 80 kilometres thick, overlying the mantle, which is hot, plastic, superheated, and the starting off of a shallow continental sedimentary basin and overlain by water, or by the shallow seas. As you get radial increase, this is transferred to the crust as crustal extension. So you can imagine this as being, say, a piece of plasticine or a toffee or something. You stretch that over a very long period of time, you get stretching and elongation. And a very good example of the rocks that would form in here are down in the foyer. If you go down the foyer, look at the floor, look out in the mall there. These gneissic rocks have a very stretched, elongate, attenuated fabric. This is typical of this environment. If you continue to stretch that crust, you then start getting faulting, what we call listric faulting along these margins. And a classic example of this is the Red Sea between Africa and Arabia, where the margins of this sea are fault bound, these classic listric faults. Continuing on with that extension process, we then get into a continental scale where we get a breakup of this and fragmentation to form the modern continents and the modern oceans, the modern ocean basins, and then migration. It's a little animal. This is another sequential animation, so I won't be able to show you this again. Leads on from that, the brief introduction last slide. The method of constructing each of these next models is to just simply take away, in each of those sedimentary basins, take away those sediments and put them back onto the exposed lands. Take away the volcanic rocks and granite rocks and put them back to where they came from. And just gradually close off each of those sedimentary basins back in time. It's a very, very slow, very minute amount of movement per year. As I mentioned, the radial increase is only a maximum of say 100 microns per year, which only equates to maybe a millimetre per year. And this is inconsequential on an Earth scale. This animation represents 95% of Earth history. 4,400 million years time history. And these are dated by modern dating techniques, so it's well constrained. The age of these rocks are very well constrained. The most ancient rocks in the world are presently about 4,000 million years old, and the most ancient meteorites and asteroidal rocks are around about 4,500 million years old. The coastlines shown on these animations, I don't know if you can see them there, outlined in blue, represent those same continental seas and the most ancient supercontinent, distribution of supercontinents, just slowly changing with time as the crustal, the size of the Earth changes. And these represent, moving forward in time, this represents Rodinia, Gondwana, as you've probably heard of, and also Pangaea supercontinents, and all the other minor continents like Laurasia, Laurussia and Laurentia, for instance. We won't go into that. And also the seas, and also the ancient seas, the Tethys, Panthalassa and Iaptus seas. And you see, as I hoped you'd see, this is very, very easy to visualise in this format, and hopefully understand. And unfortunately, from a plate tectonic point of view, where we have a static radius Earth, and that yellow circle, by the way, is the present Earth, the radius of the present Earth. On a plate tectonic concept, we're led to believe that these fragments of continents randomly assemble and collide and disassemble in a random motion throughout the world. So we have this wham bang crash bang scenario, and as I hope you can appreciate that if that were true, then you cannot assemble these fragments back in time as I've assembled them. It's a physical impossibility. So this is what the primitive Archean Earth looks like. The radius is around about the same size as the Moon, the present Moon, about 22% of the present Earth radius. And this one model represents the Archean to Mesoproterozoic, and that's about 4,600 million years ago to 1,600 million years ago. And if you recall back on that graph, that interval of time, we're only dealing with microns. A change in radius is only micron scale. So this one globe represents, that time interval represents about 60 kilometres change in Earth radius. And an Archean model would not look any different to that model there. So what's shown here is an assemblage of the most ancient crustal fragments in each of the present-day continents. Australia is well endowed with these ancient fragments, the West Australian shear right up into the Kimberley, Central Australia. Each of these fragments are represented here, whereas Eastern Australia are young, essentially young sedimentary and volcanic rocks. So on this concept, the expanding Earth concept, this material has been removed. The sediments have been returned to the ancient continents, ancient continental crustal fragments. As I hope you can all appreciate, this is where they came from. They're eroded, mechanically eroded, and been washed down the rivers and deposited in these sedimentary basins. So all you're doing, moving back in time, you're just simply returning them back to where they came from. And similarly, the volcanic rocks, they come from the mantle, so you just simply return them to the mantle, and the granites and the water and so on. These are what's left. These crustal fragments are what's left, and as I was alluding to before, on a plate tectonic scenario, this would be an impossible situation where these same fragments are being wham, bang, crash, bang, and colliding into each other and then breaking up and dispersing at random, willy-nilly, all over the world. And as I mentioned right from the start, plate tectonic people do not use this oceanic mapping, so they cannot get to this level of confidence in reconstructions. Also shown on there is an outline of the location of the present-day continents, which you won't be able to see, but just flashed past was Antarctica, Greenland, Hudson Bay, so that's America. Just trying to sneak down the side there. So America, and Australia is tucked in there, Antarctica, India, etc. This is the complete sequence from the most primitive Earth moving up to the present-day Earth, defined by that yellow circle, and also moving into the future. So it's not defying any premise. We're just simply, in this case, we're simply now eroding the material into those sedimentary basins. We're introducing new volcanic rocks and granite rocks, just progressively stretching that continental crust, progressively very minute amounts each year, progressive extension, and collapsing that crust to form the mountain belts and seismic areas of seismic activity, volcanism, and so on. And also that, you won't be able to see, but that network of sedimentary basins also represents a network of crustal weakness, which will then eventually form that network of mid-ocean rift zones. If you just hold that there. A very, very interesting outcome of this research was the problem of extinctions, and around about the same time as I was doing this research, of course, all this cometary impact and meteoric impact studies came into vogue. At this particular moment in time, the Paleocene, which is around about 60 to 65 million years ago, the dinosaurs became extinct at 65, finally became extinct, and also 90% of most faunal and floral species as well became extinct at 65 million years' time. So that's the time at this moment in time. If we were able to rotate this one globe, you would notice that there are actually, at this time, there are actually two separate, distinct oceans. The Atlantic plus Indian Ocean, the primitive Atlantic and Indian Ocean, and a completely separate Pacific Ocean. Each of the continents are joined, Australia to Antarctica, Australia to Asia, and the Americas and so on. So these are land bridges which completely separate these two oceans. So you have the potential to have separate sea levels, separate salinities, separate temperatures, separate currents, separate fauna and flora within each of these two oceans. When we move forwards in time, Australia and Antarctica then started to break up and rift apart at this moment in time. And I might add the demise of the dinosaurs and these fauna and flora species occurred over an 8 to 10 million year time period. What we're being told is this was instantaneous. This meteoric impact was an instantaneous event. This is absolute rubbish. If you go back into the paleontology, this study of fossils and the dinosaurs' extinctions are very well documented, and this is all substantiated by plotting these dinosaurs, the locations of these dinosaurs on my various models. And it shows that at this moment in time, Australia, you may be able to see that between Australia and Antarctica, you then start to get opening up of the and formation of the Southern Ocean. So in other words, what I'm alluding to is the ancient Atlantic and Indian Ocean then drained and filled up the Pacific Ocean. So you get this scenario where dinosaurs and various species living around the margins of these two oceans, their habitat was drained over, geologically speaking, a relatively rapid period of time, 8 to 10 million years. Similarly, in the Pacific Ocean, their habitats were flooded. So, of course, the dinosaurs and all these species are specific to these environments. So one it became extinct because their habitat was drained, and the other became extinct because their habitat was flooded. And ever since then, the two oceans have been equivocal. Prior to that, there's also another minor event earlier than that, where the primitive North Pacific and South Pacific oceans were two separate oceans. So Australia and America were joined together here, right here at Brisbane, and Californian coastline were joined together. So we had two oceans, the North and South Pacific oceans, and that moment in time that fragmented and the two oceans merged. We had another mass extinction event, and there's been a number of these through time. Okay, look, I'll just leave them as statics on the screen now. So I think you can get the gist of what I'm trying to get across is that modelling this crustal, the oceanic and continental geological information, this mapping, demonstrate that an expanding Earth is indeed viable. I came to a critical point in my research at this time. I could see that hey, all this information said that yes, the Earth was expanding. So, but what happens to the various data sets that are now readily available, the crustal geology which we've dealt with, the ancient magnetic poles, the location of the poles, the ancient geography, the ancient climate, and also we'll then allude to mechanisms for expansion. When you plot this information on each of these globes, if this information doesn't work, well then I'm obviously wrong. As I found out, what I would have liked to have shown here is the development of Australia as an example of crustal geology. Australia, this is the location of Australia now. Moving back in time, Australia is actually located in the northern hemisphere, and is also rotated in a north-south long axis. It's distinct from an east-west orientation at the moment. So the bulk of Australia is in the northern hemisphere. Perth is in high northern latitudes. The ancient equator runs through, say, Adelaide to the Northern Territory, and Queensland is just tucked down into the southern hemisphere. And that's where it stayed for 95% of Earth history. As we move forward in time, with the opening up of the ancient Pacific Ocean as well as the Indian Ocean, Australia then rotated and migrated south to its present location. Geographically and climate-wise, this is adequately substantiated, especially in West Australia, where we have extremely deeply weathered rocks. We have what's called laterites, which are a valuable source of aluminium and iron, which only occur in equatorial and tropical equatorial climates. Similarly, we have, overprinting that, we have a period of desertification. Most of Western Australia and Central Australia is now desert. So from that tropical environment, as we move south, we then steadily move into a desert environment, desert climate. Anita and I have just spent the past week travelling through the hinterland here, to nearly 2,000 kilometres, seeing your wonderful state, and through all these national parks and whatnot. The common theme, these palm trees and ferns and these ancient plant species, wherever they come from, why are they there? These indicate to me that that was a tropical climate, and that's precisely what this modelling is showing, that Australia, as well as those of you who've been to Alice Springs and say the Bungle Bungles, for instance, there's remnant palm trees in there which just should not be there. In plate tectonics, Australia is supposed to have been originated from near southern South Pole and migrated north, and is supposed to be still migrating north. So where have these palm trees come from? Here we have a situation where it started in the northern hemisphere, crosses the equator right at that moment in time when these species are evolving and becoming widespread, and then migrating south into a progressively more drier climate. So in these little niches, Alice Springs, Brisbane, Bungle Bungles, these niches of remnant tropical species. For those of you who have travelled in outback Western Australia, you also see pine trees and cypress pines which are just totally alien to Australian climate and vegetation. On all of these models, you will have noticed that I've plotted an equator and also, by inference, the poles. This pole data comes from, there's a global, international global database of ancient pole data. And the ancient magnetic poles are, without going into too much depth, all volcanic rocks contain minute iron minerals, the magnetites and the hematites crystals, and when they solidify, that magnetite in particular will have a polarity that will have a north-south pole and would be lined up with the ancient pole. So if you then come along and take measurements on these on this remnant magnetism, you can then get an indication of where the ancient pole was. And when you plot all of this information on my models, you get a diametrically opposed north and south cluster, polar cluster, on each and every single model. And from there, it is just simply a very simple process of scaling through 90 degrees to determine the equator. This is the North Pole. It should, by right sequence, through to the present day. That is actually located in Mongolia and North China. You have, that's Antarctica, Greenland, North America, Australia's in here, I think, from memory, in here. Bearing in mind that Australia was north-south at that time, so it's nipping into the northern hemisphere. When you sequence through time, that pole, the actual pole, stays in the same place throughout Earth history. That's one thing that came out of this research. The actual pole, both poles stayed in the same place. It's the actual continents that move around. As the oceans open up and the radius changes, you're getting this apparent migration of the continents, an apparent migration of the pole. So the North Pole commenced here, was in Mongolia, North China, for 95% of Earth history, and briefly migrated into Northern America, and then back into the Arctic Ocean where it is at the present. Again, this is the ancient South Pole, and that, what you can see on the screen, is Africa. So this is Africa, again orientated sideways. This is South America, tucked in. The Atlantic Ocean will eventually open up at that join. This is India, Madagascar, and Antarctica, and remnants of Europe up here. So the South Pole was located in Central West Africa throughout 95% of Earth history. As the continents started to break up and the new oceans formed, that apparent polar wander was down through along the west coast of Africa to South Africa, and then during the Mesozoic, which is the era of the dinosaurs, it then migrated across the opening Atlantic Ocean onto Antarctica. Antarctica, bearing in mind, started off in the equatorial regions, and it migrated underneath the pole, underneath the South Pole, and at that time there was a change in climate. So as the pole, this would have had quite a large polar ice cap, and as it migrated south and the Atlantic Ocean opened up, this ice cap was disrupted. As the pole then migrated across the Atlantic Ocean, it became seasonal. With the warm ocean currents, that would have melted that ice cap and became seasonal, hence the change in climate. And once Antarctica started encroaching on the South Polar region, it started to get fixed permanent ice sheets developing on Antarctica for the first time. Antarctica has then subsequently continued to migrate through the South Pole, so we have the South Polar ice sheet concentrically contained within that continent. The change of climates, this media announcements that the South Polar ice cap is melting, and we're entering into a change of climate. I don't take much notice of that, because when you consider that Antarctica is migrating underneath the polar ice cap, what happens is that ice cap is, or the continent is trying to drag that ice cap along with it. So what will happen on the leading edge, that will break up and fragment and melt, just exactly what they're showing us on television. But the other side, which we're not shown, will then refreeze and reform. So the ice sheet stays relatively the same size, but it's trying not to be shunted sideways with this continent moving underneath it. And similarly, as it migrated out of Africa, the exact same thing was happening. And when you plot climatic data and distribution of species on there, the same things are happening, and these species are trying to move around, getting away from these changing and evolving climatic zones. Again, what I would have liked to have shown here is the progression of each of these ancient continental seas. The blue outline shown there as the coastlines, and as you change the radius of the Earth and change the configuration of this crust, and also the quantity of ocean waters, you get a variation in the coastal outlines. And this, over the period of time, you then progressively evolve from the Rodinia to Gondwana to Pangaean supercontinents and all their subcontinents. And this coastal information was plotted from published information, published readily available global data. There was no manipulation of the data, and it coincided precisely with the distribution of these sedimentary basins, as you'd expect. The sedimentary basins, because material is being flushed into these shallow seas. Moving forward in time, as this crust extends and then finally ruptures and starts to break up to form the modern oceans, you then see in the data a reduction in the area of these continental seas, which implies a draining of these seas into the modern oceans. The formation of the modern oceans, then you then start getting the mid-ocean rift zones opening up, and with the mid-ocean rift zones and the new volcanics, you're getting all this new water being expelled, and as well as the gases, and so you're again getting a flooding and a filling up of these modern ocean basins. It's quite dramatic when you see it properly. The climate zonation can be modelled by plotting what we call climatic dependent indicators, the limestones and the coals and glacial related rocks, and say evaporites like salt and so on. You plot the distribution of these. I've only shown coal and reefs here. The reefs are in stars and the coal is in diamonds. Coral reefs only occurred between, say, 20 to 30 degrees north and south of the equator. So you would expect that limestone coral reef data would plot and straddle the equator. And this is precisely what this shows. And similarly, the coal occurs from the equator to sort of more temperate zones. And while it's not immediately obvious here, when you rotate it, you can see a little bit better. What the data also shows is there is a shift in the data. There is a northward shift in the data. It still parallels the equator, but there's a shift in the data, and you can explain this by, at this time, the Permian was quite a major ice age over 10, 15 million years, and that was a permanent ice sheet in the southern hemisphere, as distinct from the northern hemisphere, where we had these inland seas, the Tethys Sea in particular, this one, stretching all the way from the equator all the way up across the pole and also over the other side. So you had this potential for this warm equatorial currents to migrate north around the pole, melt the ice caps, and so you just simply get a seasonal ice cap developed similar to the Arctic ice sheet at present. hence a much smaller ice cap in the northern hemisphere and a shift in these climate zones. We're just coming to the bit that you're all probably waiting for with bated breath. Why? How does all this occur? And what I'm about to show you is speculation, because this question has never been required to be asked. As you can appreciate, if you're led to believe that we have a static radius Earth, we live in terra firma Earth, there's no need to ask the question as to how could it possibly expand, where would all this material come from. Hence, there's only a handful of researchers throughout the world that have even bothered to question this. What I've shown here, I'll leave it up to you to read it. Modern technology is such now that we can accurately measure the dimensions of the Earth from satellite laser ranging and various other techniques, and also measure the plate motion, the migration of the continents on a yearly basis, down to sub-centimetre levels, accuracies. This has been going on since about 1976, but it wasn't until 1993 when they had enough ground-based stations available throughout the world to be able to use this information, this 17 years worth of information, to calculate a radius of the Earth. And what they found, as you can see there, they found that the Earth was expanding over this 17-year time period. The Earth was expanding by 18 millimetres per year, and my calculations are 22. So when you take into consideration the error factor, which is about 3 or 4 millimetres, it's pretty well spot on. NASA was spending, at that time, NASA was spending something like $500 million per year to prove that the Earth, well, not prove, but independently prove that plate tectonics was the way to go. And so, as the last statement maintains, that this was basically considered an error, and they recommended this be restricted to 0 because this is closer to the true situation than an average of 18 millimetres per year. So in other words, they were not anticipating the Earth to expand. These measurements are extremely sophisticated mathematics and statistics taken from over 600 ground-based stations from around the world. And these are all fed into a supercomputer in Paris and spat out the other end. And if you delve deeper into their literature, you'll come across modifications, little tweaks to the mathematical formula to eliminate this error. So they didn't even suspect that the Earth was expanding. So basically now, when I get questions on, yes, but NASA is measuring the size of the Earth and it's showing that it's not expanding, when you go into their website, you will see that the mean radial increase in radius is less than 1 millimetre. It's just purely simply a manipulation of mathematics. I don't know if there's any mathematicians here, but you give a mathematician or a geophysicist or a physicist a set of data and he'll manipulate it to whatever you want. It's true. Then we're posed with the question, okay, the Earth is increasing, the information suggests it's increasing, so is it an increase in mass, or is it a constant mass and an increase in, say, density, for instance? To cut this one short, the top two curves are a constant mass scenario, and it would suggest that during the pre-Cambrian, the primitive Earth, say density and surface gravity were extremely high, which is extremely unlikely. And these figures, say 15 times the present, 15 to 20 or so times the present values, these just do not occur in the solar system, elsewhere in the solar system to date. So this is just pure mathematical manipulation of the radius data and the radius formula that I showed you, certainly the graph that I showed you early on. So we're faced with the suggestion that increase in Earth radius is caused by an increase in mass. So where did all this mass come from? I don't know. But this is a speculative mechanism that I developed and put forward in my thesis. What the geological information tells us for the very early Archean era was that certainly mantle temperatures were around about 1,500 degrees hotter than what they are now, and surface temperatures were between 30 and 300 degrees hotter than what they are now. I'll just briefly mention something about geological time before we go on a little bit further. Geological time, to measure geological time, there's certain minerals that you can assay and determine they decay. They're decay products, they're daughter elements. You can measure the ratios of these, and you can then convert that to time. You know the decay rate of these various minerals, and there's a whole suite of minerals that you can use. And these methods are very, very sophisticated these days. I work at Telfer in central north West Australia at the moment, where our rocks, we have granites, they're dated at 604 million years old, plus or minus 1 to 2 million years. And this is very, very accurate compared with 10, 15 years ago, where that would be 600 plus or minus 20 or 30 million years. So it's becoming very, very sophisticated and very accurate these days, but I digress. So what I was alluding to is you can only measure the age of a rock once the crystals in that rock have solidified, and that rock has cooled enough to be preserved with time. So at that moment in time when that first rock solidified and was preserved up till the present day, and you then go and measure that, take measurements from that. Prior to that time, if that rock was molten, you cannot measure time. So basically our geological time starts at that moment when that first rock crystallised and solidified and preserved to the present day. So these high mantle temperatures and surface temperatures then suggested to me that during the pre-Archean, prior to 4,500 million years ago, for an indeterminate period of time, that the Earth was actually molten. And what I've shown here in this first one is a slightly larger Earth, an Earth plus Moon incandescent blob. And what I intimated in my research was that the Earth, this primitive Earth-Moon blob, was very much closer to the primitive young Sun, very much smaller than what it is now, and totally different to what it is now. So if you can imagine a fragment, or not a fragment, a blob of material flung off the surface of this primitive young Sun, very similar to the sunspot activity that we see today on a yearly basis, happening on the Sun today, but different materials. So what I'm suggesting is that we have this whatever the Sun is made of, this blob of pure energy, whatever, plasma, whatever, that's flung off this surface of this Sun. That blob, as well as periodically the rest of the remaining planets, are also the same. This material, this primitive planet, along with the other planets, then gradually, over a very extended period of time, move away from the surface of the Sun, away from the influence of that high temperatures on the Sun. This material, this energy, then simply condenses to form matter. This is simply a reversal, as our next speaker I think will allude to. This energy, in Einstein's equation, if you increase the speed of matter, you convert it to energy. If you decrease the speed of energy, you condense it to form energy. It's just simply a reversal of Einstein's equation. Energy has no mass, or matter has mass. So at that moment in time, once that energy condenses to form matter, you then start to get mass. During this same phase, I envisaged this newly formed material condensed on this very primitive blob of Sun material, becoming gravitationally unstable, or generating a wobble. I calculated that if you need 400 kilometre thickness, which is about that scale of material, of this new molten matter, to be stripped off that primitive Earth-Moon blob to form a binary Earth-Moon planet, which is what we are now, a binary planet. The size of the Moon and the size of the primitive Earth were roughly identical dimensions at that time, 1,700 kilometres radius, 3,400 kilometres diameter. We'll forget about the Moon now. That Moon comprised matter which had already been condensed. So the radius of the Moon essentially stayed constant from then on. The Earth was still retained this highly reactive core material. I then envisaged this condensation of matter to continue to condense at the core mantle interface. New material will then forming the mantle. New material will then cause mantle swell. Mantle swell will then be transferred to the outer crust and cause crustal extension. By the time we get to the Permian period, we then reach a point where this newly formed continental crust, the ability to extend is exceeded, and we start getting fragmentation and breakup of this crust and opening up of the modern oceans. And this is a cross-section of the modern Earth, where we have mid-ocean rift zones, volcanic material being derived, upwelling from the mantle, being extruded along these cracks and being solidified on at the ocean floor. The fragments of the continental crust remain in position with deep roots. This is again a contentious issue in plate tectonics. The continents have very deep roots, where in plate tectonics this material is supposedly subducted in this very region where we have these deep roots, very, very deep, hundreds of kilometres deep roots below our continents. So that's in a nutshell. My summary is, yes, the Earth is expanding. I hope you can appreciate that. I apologise for the muck-up in those video animations. I'm really disappointed in that, because as I said before, it worked fine when we tested it there. All of this is now available in book format as an e-book on www.oneoffpublishing.com, and our hard copy book is printed. It's supposedly in transit, and it's being distributed through most of the university bookstores. If you're genuinely interested in purchasing a copy, see the lovely Anita there, and she'll take your details and certainly forward you a copy in due course. I would have liked to have shown this as a finale while I answer questions. We'll just see if it works. Yes, plate tectonics. Yeah, yeah.
It's lunchtime.
Yeah.
Give him a big hand. Thank you. Thank you, James.
Thank you.
Yeah, thank you, James. We may just leave that up and let it run for a while for people who want to have a look at it. James will be out there to answer any questions. Are you going to have any of those animations on your website, do you think, as a lower res and GIF animation? It's something to consider, because they're very descriptive.
If you're genuinely interested, just contact me and I'll send you a CD.
Yeah, he's saying if you're genuinely interested, contact him and he'll send you a CD. And I really think it's most interesting. Give him another clap. That was pretty stressful to go through. And thank you for your patience too. Just before you all go, we're about to break for lunch, so anybody who's absolutely starving, feel free to dash out. But I just wanted to point out one very interesting little piece of information. You recall he mentioned the continent of Antarctica started off in equatorial regions, or a little bit higher, in between what's now Europe and the Americas. And I know there are a lot of researchers who believe that there was once a continental landmass in between Europe, Africa and what we call the Americas today, which is not there. We know that from cultural things. A lot of people here in the audience are probably aware of the legendary continent of Atlantis. Well, there is more than one researcher out there who have a very good case to suggest that continental landmass is now what we call Antarctic. There's one guy there, Rand Flemath, who's got a whole book based on Atlantis being where Antarctica is now. So it's a lot of interesting school for, things for thinking about there.